Hi, everyone. Uh, Hello. Today, we're going to talk about what we started last time by using just a simple polygon and helping a student to understand many attributes of a polygon, but just using a simple one. Last time, we measure um, line segments about in shapes such as a pentagon, and today we're gonna move forward to do angles or maybe pair of coordinate pairs, or and then maybe perpendicular lines or intersection lines, all the details that we can show by just exploring one figure. Okay, just a moment, I need to change this. Okay, I think I'm gonna try to do that using a sphere now. Okay, sorry for that, but we can start. Last time we had this pentagon and we measure each side into centimeters units, and also we measure it in inches, and we find equivalent in fractions of 4/16 to 1/4 of an inch, and then line segment AB, BC, CD, and DE, and EA. Another idea is just using those links and teach students how to calculate perimeter, because perimeter is if you add all the lines around the figure, and that is the perimeter of the figure. So that's another idea how to use this. But to start with, we've got this polygon is in a quadrant 1, which both axes are positive. X-axis is positive, and then y-axis is positive as well. So we're going to start with maybe A and figure it out. First, if we want to find a pair of coordinates, the x goes first. And then from the point A down, we can see that if we take a little dashes, we can see that x is 6. So we can open parenthesis, x is 6. And then from that point, we will go to the y axis, and y is 9. So coordinate pair for A is 6 and 9. And then for B, x is 13, and then y is 7. Okay, for C, C is the same as a B for x. That would be a 13 because they're on same line segment. And for y is 3, which is same for a D. I can put it on this side because I don't have a room, but that's okay. X is 10. and y is 3. Okay, and finally E, x is 1 and E is 6. Y is 6, sorry. Y 6. So that's another way of to find the coordinate pair. Another idea is to add, let's explore angles. And last time I was trying to, and my screen froze, but I use a sticker to just explore my angles. So if I take this one here first, it will exactly match into the my sticky notes, so I know that that must be a 90 degrees angle because it's perpendicular lines and they are creating 90 degrees angle. So as now I can right away see that this is right angle. Right angle usually is because it's created a square. It's labeled like this, and usually it's just a little square. When you see the symbol, that means it's a right angle. Another way I can explore is with my small rectangles, triangular rulers that I can put in, and I know that this is 90 degrees angle because it fits perfectly. Um, I can explore the rest of my angle. So if I already know that if is right angle, it has to fit to my corner. So I can see right here that this angle is much bigger than a little bit bigger than 90 degrees. I can see if I take this one here, if I wanted to be my angle to be a 90 degrees, I can see the line, this line segment should be here, but it's not. It's about right here. So that tells me that my angle is smaller than 90 degrees. If I take that page right here, the right angle is right here. So it's this angle is greater than 90 degrees. It has to be that obtuse angle. I also would like to touch some things that kids don't understand, that the angles are actually in a circle. So if I take point B and I make circle around it, I can show them that actually my angle is in a circle and I have inside and outside angle, and then inside of the shape angles will add to outside angle, they will make a circle altogether. But as now my angle inside this angle is can represent from, it's around point B and it's made of line segment AB and BC, BA, BC. Okay, so I can measure that angle and I can see that is part of a bigger area of a circle. I also can do that same thing around for A. So if I drew my compass around each of these points, I can see right now that my angles are smaller or bigger part of a circle. You can right away when they see how big is a circle, they can see that if angle is greater than 90 degrees or less than 90 degrees, this angle is taking much more of the circle than this. So this angle should be a smaller angle, and of course, and then if I take this one right here. I can see if I compare to all circle that it takes lots of space, and we can also color for kids so they can see that's the idea of part of a circle is each inside of this angles in this polygon. Also, if we add all angles in a triangle, we gonna have 180 degrees. We can talk about that. And then if you add every quadrilateral will give us 360 degrees. Like adding. So when we find out angle, now we can measure them. The first one, of course, this is 90 degrees. I can say we can label or not, but this symbol should already tell you that is 90 degrees. So if I already check with my that it has to be bigger than 90 degrees. So I have to find out how measure or exact. So if I take my protractor and I am measuring on my center of a circle is in the middle on just on a B. I'm looking where is the zero line, it's right here, so I'm looking for 0, and it goes all the way to the segment BAE, and as I can see it's going from 0 all the way to 100, and then 105, 106, 106 degrees. So we can measure, and that would be 106 degrees. Okay. Then if I go to measure this angle, I can also put my center of a circle on a point A, for example, and then I can go from segment AB to the segment AE. And also I'm looking if this is a 0 line, that means I have an outside measures, not inside measure. I'm going to use where 0 is, and 0 is right in here. Okay, so that would be a 0 all the way to here is 130, 131, 32, 33, 133, or 34, 134, about 130. Okay, 1, 2, 3, 4, 134. So 134 degrees. Point E. Of course, there could be a little bit because the lines are thick and precision is not as great as it should be. So let's see. Now I have my point, my protractor is, the point is on E, but my 0, it's a 0 line. It's not anymore outside, is inside. And then kids needs to see that the 0 line is right here. And then 10, 20, 30, 40 is about 50 degrees. This angle is less than 90 degrees. It's about 50 degrees measure if I measure it. And then angle D, okay, 600, just the one. Okay, oops. And if I put here on a G, now I can think about this extend line, but I'm going to take that point D and all the way to this line here. So in order that if I cannot see the line, I can extend the line. For example, if I need, I can extend this line in order to measure this angle if I wanted to measure it from that side. I forgot to say that angles could be measured on either side. I can measure angle from this side and I can measure angle from other side. It's because it's in a circle, it's a part of a circle, you can go either way. This time I'm going to use that as a zero line. I'm going to all the way outside. Inside is a 0, so 0, 10, and I will go all the way to 160, 160, 1, 2, 3, like 163, something about 160, 100, approximately 163 degrees. Okay, so when we measure these angles, that kids can understand that there are the parts on the other side as well. We can explore diagonals, we can explore, but what I really would like us to explore is the lines, the line segment. If we extend those line segments, how they behave. So if I extend this BC line segment down, I can use a different color. So if I extend BC down and then I extend DC, I can see that these two line segments are perpendicular to each other. So as you can see, here is a perpendicular they create 90 degrees angle, 90 degrees, 90 degrees, 90 degrees, 90 degrees. So these two line segments are perpendicular. We also can use our knowledge of writing it down as a symbols, how you can say. So if I use this margin down on a B, I can say segment BC, and that is how you line up. It's a little line above BC, so I read it as a line segment BC is perpendicular. This symbol is perpendicular to line segment DC. You can say CD or DC. It's the same length, so it's so we can say that these two are perpendicular to each other. I'm wondering if the lines AB and ED behave as parallel lines, because it looks like if I take my ruler and make a parallel to the line segment AB, I can use my small ruler and I can use, if I make very strong one of my orange ruler, I can with one finger and make the green one parallel to AB. I can easily move my ruler up and down and see if these lines are perpendicular or parallel, sorry, parallel. And they kind of, but not really, almost. It's not perfectly, so I can see that they almost parallel, but they're not perfect parallel. And if I look this line, they're not parallel. They're intersecting each other. So none of the sides are parallel. So I can use if AB would be parallel to ED, then I would say I will label it as line segment AB is this symbol parallel to ED segment, but it's not. So it's not parallel. So I cannot uh, say that 100% that it's a parallel. So if I look these lines X and X plan, I can see that segment AB and segment BC, they intersect, but they are not intersecting in as a perpendicular. They just intersect. So these two angles are congruent. 106 degrees is this one, and then outside angle should be as well 106 degrees. So when we know that, it's easy for us to figure it out. The length, the size of these two are obtuse, inside and outside, and then you have the two acute and two obtuse angles. We also, for kids to memorize it, we can even write obtuse, like obtuse. This one is also obtuse. Okay, this one is obtuse. And this one is acute angle. Acute angle. Because this is obtuse, these two are acute. And we can easily find out because they're also congruent. So if this one 106 and this one is also 106, we can add them up on the side, and that would be remember 212 degrees are these two, but all of them should create 360 degrees. So we know that whatever it's left up to 360, it would be sharing these two angles would share that measure. So what we need to think is 212 plus what? It will make 360 degrees. That's one approach. So you can think about number would equal to 360, or we can use the subtraction and say 360 degrees minus 212 will give us the angles that these two acute angles will share. So I can, if I have 0, I cannot give 2 away. So I have to regroup the tens. So I'm going to have a 5 tens, and 1 10 will be becoming 10 ones. So I'm going to take 10 ones. Now I can give 2 away because I have 10. Before I had 0. Couldn't give away 2. So 10 minus 2 equals 8. 5 minus 1 equals 4. And 3 minus 2 equals 1. So what that tells me that these two are sharing 148. And now we have to find 100 and half of 148 to divide into 2. Very often kids have a hard time to figure out what is a half of something. So if I decompose 148 into 100 and 40 and 8, I can easier to find half of it. So half of 100 is 50, half of 40 is 20, and half of 8 is 4. So practically half of 148 is 74. So each of these, we find out that they have to be 74 degrees if we did correct. So you can do all these angles. As you can see here, it's 90, 90, 90, and 90. So that means that all this is 360 degrees, and then we can talk to the students about it. Another, we also can show dashes if we show them how obtuse is, that we know that it's obtuse. We can create for each angle, we can create how, if it's 90 degrees, the line would be right there. Here, if I put parallel to the edge of EA, if this angle would be a 90 degrees, it would be this much, but it's greater, so it's bigger than 90, so that's 160. If I look this one here, and I measure my line, if this angle would be 90 degrees, my line would be right here, but it's not, it's less than 90 degrees, so that is acute angle. This one here, if I make a parallel to DC, if it's 90 degrees, it would be right there, so it's much bigger, and that is 163 degrees, how much we measured. Okay, what else I can, you can also, thinking what else we can do in this. That's just like for now, but like you can think about area or in perimeter of this shape. Area could be found in two different ways. So I'm going to use a different paper, the same shape but a different paper. So if I take that one, okay, give you idea what we do. Just a second, please. Okay. If I have the same polygon, and I told my kids how we could do perimeter or area. Of course, perimeter is I measure already before, and I can add the sides equally, so that would be for them easier to find. But when it's about area, then it comes to the more difficulty. So there are two methods that you can use. One method is that you can cut this shape into the equivalent squares, and then you can figure it out inside how many squares are inside. Or you can create a big rectangle around that shape, and then you will take these extra parts, and then you will figure it out. So the one method is called inside method, and other one is called outside method. So if I already create kind of line so that it's easier and save us time. So first I'm gonna help you how to do inside method of finding area. So first thing what I would like to do is to create, I put this grid created, and then I am going to cut this shape into the small rectangle, small squares. So I would like to see how many whole squares I can really count. And then what am I going to do with the rest of it? And then that's the first. Okay. Okay. It's good enough. I hope you see that better. Okay, I'm going to just highlight every whole square, so I can see this one is whole and all that because it's right triangle. I can't right angle, sorry, right triangle. I'm talking, so you can see this as well. So far, I have highlighted all that are whole squares. And then I notice pattern here that I can use because I teach a student that every rectangle or parallelogram is created of two equivalent or congruent triangles. So I can see here that this is one triangle that I can see. If I create around that triangle, around it rectangle, I can see that if I look, my rectangle would be 1, 2, 3 units, squared units. So because this rectangle is 3 units, half of rectangle is my triangle. So the half of my triangle must be 1.5. So I'm going to use different color just to make sure that you can see that triangle that is right there. So if I'm looking, that is 1.5 or 1.5. I can also use different, I can use 1.5 or I can use 1.5 or I can use 1.5 if I use a fractions. Okay, now I have a similar on the bottom, so it's almost the same. So I'm going to use that as well. And it would be a 1.5. That orange space is 1.5 units. As well, I can see right here, because if I look, can think about, you can see that this is part of the 3 units, and that is how I can figure it out, that that is 1/2. And have another one here, which is going to be as well 1.5. Okay, and then I have right here this one. Okay, take it. There you go. 5. I have this top of it. It's about, if I think, then missing. So this is going to be about, it's like 2. So these are 2, but this part is also that could be about 1, because 2, when you cut in half, it's about 1 unit. And then this could be only half a unit because it's just about half. I'm saying about because the picture is not perfectly aligned, so we can say that this would be a 0.5 or a half a unit. Okay, and then the top of I can see it, I can break it into actually two parts. So I'm going to make this part, this triangle, that would be a 3, and we can see that's 1, 2, 3. So the triangle is 1.5. This part right here. And then you have this part here. That would be, if I make a rectangle around it, that should be about 1, because if I create rectangle around is 2 units, and now the 1 unit is just 1 part. So now you have an inside method, and you can just add all these values together, and you will be able to create to say what area of this pentagon is. So we can use space right here. So area is equal, and if I count all these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. It's 29 square units, and that's, and then if I combine, we'll have 1.5 and 1.5, that would be 3, and then these two will be give me another 3, so that's a 6. And I can say that this 1.5 and on this 1.5 will give me another 3, so 3, 6, and 3 is 9, plus 1 would be a 10. So 10 in a part, then total would be 39 square units. 39 square units. If I think about these to be a centimeters, I can make it, but they're a little bit greater. So we square units. So the it could be square centimeters or square inches, and we using abbreviation as like square centimeters or square inches or square feet, square meters, all these different units that depend what is needed. So that would be a inside method, sorry. And now we're gonna explore outside method and see how it works. Okay, so now I'm gonna take the same figure, and outside method is going to give you idea that you will go and you will make rectangle around your shape. So if I take this and I just surround this shape with lines, I can create a great larger rectangle that surrounds this shape. So now by using the formula about length times width for rectangle, I can figure it out that large area of large rectangle is equal to length times width, which is length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 units times 1, 2, 3, 4, 5, 6 units. So that should be an 66 units. 66 square units. I'm sorry, didn't. So area of that large rectangle is length times width, and 11 times 6, which is 66 square units. Now, because we know now all of it, we would like to know just the inside shape or figure. So we have to take off these parts or these big triangles away from the total in order to figure it out what that is, what the inside area is. So if I take and just highlight parts, then I will take away that will help me to figure it out what would be what I needed to take away. Okay, so I can see this triangle. If I try to make a rectangle around it, I can use my little dashes, and that will show me that this rectangle is 2 by 2, 4, 6. 2 times 6 is 12, but half of a 12 is 6. So this is a 6 units, a squared unit. And then same thing if I do this one here and I create a rectangle. So it would be this rectangle right here. So it would be 1, 2, 3, 3 by 2, 4, 5. 3 times 5 is 15, and a half of 15 is 7.5. 7.5. And then this, the longest one is going to be, okay, so if I look, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 3 is 27. And half of 27, it should be 13 and a half. So this is 13 and a half units. So all I need now is add these extra parts. So that would be a 13 and a half and 7 and a half and 6. It's really important to mention to the students that if you're going to add decimals, they need to be aligned. So you're adding decimals in your answer, your decimal needs to be aligned. If I drew the line through it, that all decimals are in the same position. So I can also add a 0 for the tens. So if they are confused, this is just a placeholder for tens. We have no tens here. We have only 6 whole numbers. So 5 plus 5 is 0. And remember 1. I always say circle around so you won't forget to add it. 3 plus 7 is 10. That's combination for 10. And then I have 6 and 1. That would be 17. 7. I remember one more. And then 1 plus 1 is 2. So I have a 27 units that I need to take away from the total. So our total was 66. So we needed to do 66 minus 27 will give us inside area. I really can say if I have a 6 things or ones, I cannot give you 7 because I don't have enough. I'm missing 1. So I have to regroup these tens and leave the 5 tens alone. And then 1 10 will give me 10 more 10 more ones. So I will have a 16 ones now, and then I will be able to subtract or give away 7. So 7, I always teach my students think addition when you are subtracting. 16 minus 7 is how many numbers are in between 7 and 16. Put 7 in your head. 8, 9, 10, 11, 12, 13, 14, 15, 16. I have 9 fingers open, and my answer is 9. So 16 minus 7 equals 9. And 5 minus 2 equals 3 because 2, 3, 4, 5. Yeah, when you use think addition strategy, that kids understand it much better. So we just figured it out that area of this inside shape is 39 squared units. This was outside method to find the area of this irregular pentagon as a shape. So that was outside method, and this was inside method of finding the area. Okay. I also can, we forgot to measure and find the perimeter. So if I take shape and just measure the sides, I can find what perimeter of that area is. And then I did that over here when we were talking about, and also I just can take a piece of paper and then I can make students understand that perimeter is if you add the lengths of all the sides. So you can make them to add length as a decimals or length as a fractions. So in this time, line segment A to B is equal to 10.7 centimeters plus 5.5 centimeters plus 4.4 centimeters plus 13.5 centimeters plus 8.2 centimeters. So I can see I have 1, 2, 3, 4, 5 sides. 1, 2, 3, 4, 5 sides. So what would be here interesting is to combine the same values that is easy to addable. So what I would do is to add mentally like 5.5 and 13.5. You don't need to do in any particular order, as long as it'll help you to do that. So 5 holes plus 13 holes is 18 holes, and half will make 1. So that means I will have a 19 of those two. Okay, when I'm done with that, I cross it off. So I'm done with the calculation. 4 and 2 are easy to add. So next I will use 4.4 and 8.2. So it would be 4 holes plus 8 holes, 12 holes, and 4/10 and 2/10 is 6. So it would be plus 12.6. And then I'm just gonna add 10 and 7/10 right there. And now I'm moving to the further. So now I can line them up, and I can do. Very important that kids know that this is 19 holes, and then you can add a decimal point to the right, and you can add a 0 for tenths and hundreds if you wish. And then you will add the next 12 holes on left side of the decimal, and a 6/10 to the right of the decimal. Also 10 holes to the right of the left of the decimal, and then 7/10 in other. So I can add a 0 if I need it, especially if it's money about. I can add a 0, but I don't need to in this situation. 6 plus 7 is 13. I also can use strategy if I'm going to add 7 and 6. I'm going to put 7 in my head, and I'm going to open up 6 fingers. So I'm taking, okay, I'm going to adding these 6 more. So 7, 8, and I'm closing fingers. So 7 in my head, and adding 6 more. So 8, 9, 10, 11, 12, 13. 6 plus 7 is 13. 3, I remember 1. 1 and 9 is combination for 10, so that's nice. Plus 2 equals to 12. And I will remember one more here. 1 plus 1, 2, 3, 4. My perimeter is 42 whole centimeters per 0.3. So it's only centimeters because I am measuring the length. I'm measuring this size lines around my shape. So that's why this I'm measuring these small lengths around my shape. That's what perimeter is in centimeter, while if I did area is in squares because I'm measuring squares. So if this is my square, and for example, if the units is, let's see, if it's like inch and inch times inch will give me in squared inch, which I'm really calculating squares that are while if it's inch, it's just the line inch. Very often kids have a misconception about when they calculate the square inches and inches for a perimeter. um, so that would be it. Can remember, it could be more, but I can really think about now what else I can. Oh, I know what else I can do. I forgot to tell you, if you have an angle, how you can label those angles. So as we saying, like this segment DC is perpendicular to the BC segment. We also can label angles as, for example, if I'm gonna label this 50 degrees angle, this is how I label like that, and then little line that represent the angle, and angle E is 50 degrees. Angle C is 90 degrees. Angle A is 134 degrees, and so on and so on. So that would be, um, this is for now, but you can also think about another ideas how you can help students to just use one simple figure and show so many attributes. Teach them angles, line segments, uh, lines, area, perimeter, and so far so good. Okay, I hope you enjoyed. Thank you so much. Appreciate it.